Okay, characteristics of polynomial functions. Polynomial functions of the same degree have similar characteristics. The degree of a polynomial function provides information about the shape, the turning points, and the zeros of a graph. Turning points are in a polynomial function of any polynomial function of degree n has at most n minus 1 turning points. The minimum number of turning points depends on the end points. So, for example, in a cubic function or a linear function, you don't necessarily have to have any turning points because the arrows go in opposite direction, whereas a quadratic has to have a minimum of 1 turning point. So does a quartic or a 6th degree polynomial. Next, the number of zeros in any function is where an odd degree polynomial will have from 1 to n zeros. An even degree polynomial will have 0 to n zeros. What that means is that you don't necessarily have to hit the x-axis all the time. Anything that's an odd degree polynomial will have at least 1 up to the number of degree the polynomial is. An even degree polynomial will have no actual zeros sometimes up to, again, the n number of zeros, n being the degree. Next part, n behaviors. What are the n behaviors? An odd degree polynomial has opposite n behaviors. For example, if the leading coefficient of an odd degree polynomial is positive, it means that the graph, as x approaches negative infinity, y approaches negative infinity. And x approaches positive infinity, y approaches positive infinity. Now, if the leading coefficient is negative, what's going to happen? Well, the opposite effect happens. As x approaches negative infinity, y approaches positive infinity, x approaches positive infinity, y approaches negative infinity. Okay, so what you need to think of is in terms of lines. Okay, so positive slope and negative slope. So what I mean here is, let's say I was to draw a cubic. A positive leading coefficient cubic may look something like this, but if you notice that the endpoints of the arrows, if I draw a line connecting the two endpoints, it will have a positive slope. This particular red cubic that I drew here would have a positive leading coefficient because by connecting the arrows right there to there, you can see that the line would have a positive slope. And the same for the negative. If you have negative slope, negative leading coefficient of, let's say, a function that looks like this in red, this function would be an odd degree polynomial, odd because the arrows are going in opposite ends, okay? But specifically, the leading coefficient would be negative because if I connect the ends, just like I did here, it would look like it has a negative slope. And you can connect the ends to give you an idea whether leading coefficient is positive or negative. All right, what about an even degree polynomial? Let's look at n behaviors for the next one. The n behavior for an even degree polynomial has the same n behaviors And this you'd have to think of a parabola. If the leading coefficient is positive, then as x approaches positive or negative infinity, y approaches positive infinity. If the leading coefficient is negative, then as x approaches positive or negative infinity, y approaches negative infinity. So we need to think of parabolas. So if we have a parabola with a positive leading coefficient, the a value is positive, we know it has to open up. Well, I could do the same and draw a quartic here. A quartic sometimes will look a lot like this. Will look a lot like a parabola, but a little more flat bottomed out to look like that. And that, folks, is a quartic, all right? And it has to have a positive leading coefficient because of the fact that the arrows are pointing up. Now remember, a leading coefficient is the number in front of the highest degree variable. So if it's a 5th degree polynomial, you're looking at the leading coefficient. The a value is next to x to the power of 5. That's the sign you look at. Now, so pointing upwards means positive leading coefficient. Okay, and then downwards, pointing downwards. So let me draw another one where you might have it. And if you think about it, all the arrows are pointing in the same direction. So I could have a quartic that does something like this. And this quartic pointing downwards like that would definitely have a negative leading coefficient. And again, negative x squared or negative a quartic, negative 6th degree polynomial, all will point downwards. Again, even degree polynomial. All right, now symmetry. Most polynomials, believe it or not, have no symmetrical properties. That means they are neither even nor odd. And the reason being is that you're looking at, a lot of times they have transformations. But to test for symmetry, don't forget that you must prove that f at negative x is equal to f at x if you're trying to prove for even. Now, or f at negative x, when you plug it in, will equal negative f at x for odd functions. Now, a lot of you are probably going, but wait, you didn't teach us that. Yes, I did. But how I set it up for you guys was I said negative f at negative x, so we plug a negative in front of f at negative x. That answer should get us back to the original function. What happens is that students can either see one or the other, but both are acceptable to prove that it's an odd function. If this is true, or this is true, so you must test for even first, then you test for odd. If it is neither of these are true, then you say that it is neither even nor odd. Remember that most polynomial functions are neither even nor odd. All right, and let's look at an example. Sketch the graph of a polynomial function that satisfies each set of conditions. So we need to draw a parabola with degree 4, sorry, not a parabola, but a polynomial function with degree 4, positive leading coefficient, 3 zeros, and 3 turning points. So let's look at the following. So we want to draw a graph that has those conditions, all right? So f at x is our function, and x is over here. And what we're going to do is draw the endpoints. Let's watch that again just slowly. So the key here is drawing each part. Now, why does the endpoints go like this? One more time. We're looking at a positive leading coefficient. So, and it's degree 4. That's even degree. So both arrows have to point upwards. Okay, and that's what they do. We need to have 3 zeros. So it has to hit the x-axis 3 times. 1 over here, 1 over here, and 1 over here. Don't forget though, you can only have 3 turning points. So when we do it, 1, 2, 3 to go all the way up here. The next part, let's see if there's another example. Okay, we'll do the same one, but we'll do a different example of the same function, again pointing, oops, sorry, this is part B now. We're looking at a degree 3, negative leading coefficient. Negative means the arrows, one has to represent a negative slope. And so if I connect this over here to this, look at the way the hand makes a negative slope. So you know that must mean a negative leading coefficient. It's odd. Odd means that both arrows are pointing in opposite directions. Negative leading coefficient, they're opening in opposite directions so that there's a negative slope. 2 zeros means it can only hit the axis twice, 1, 2, and 2 turning points, 1 here, 2 here, and you keep drawing away there. So that's another example. So you need to know how to draw functions given certain instructions. All right, folks, that's the end of this video. Take care.